Okay, I think we're set up. These buttons actually are the opposite of what I expect them to be, so I'm sure I'll be going back and forth. Sorry about that. So this is a paper called Markovian Elections. It's co-authored with Jean-Guillaume Ferrand, who visited the Wallace Institute last year, and he's at University of Waterloo right now. So you can guess from the title that we're thinking about dynamic elections. And our goal, there of course are existing models of dynamic elections. What we would like to do is to have a framework where we could think about a state variable that evolves endogenously and depends on the policy choices that are made over time. So the state variable could be a state of the economy, it could be the location of the median voter. It's pretty easy to brainstorm things you could do if you had a state variable. And at this point, we have a lot of possible applications in mind. You're not going to see any of them. I actually can't get to them in a 90-minute talk, so I'll be focusing on the theory part. And our goals are, first of all, a general framework so that people could look at special cases of this. We want it to be viable in the sense that we have a general existence result. Right. The worst thing is you have an application in mind, but then you have to go through and prove existence and have a 20-page appendix. So ideally, we would take care of that. And usefulness just means that we should be able to solve special cases and draw some insights from that. So that's what we're trying to do. Just to give you a vague idea of the model before I go into the details, we're going to be thinking about an infinite horizon discrete time model. This big circle here is supposed to indicate one period. So that we start off in some state S, and then there's going to be an office holder who's an incumbent, and he's going to choose some policy. That's the pie shape there. And if he chooses, say, policy X, then there's an election to decide between the incumbent and a challenger who's just going to be randomly drawn. And then, depending on the outcome of all this, we're going to transition to a new state, or maybe we stay at the same one. Okay. I haven't said anything about information here, but I will. But just to let you know, we're going to assume that the office holder's type is observed. So it's going to be a complete information model. The challenger will be drawn according to a distribution which is known, but their type will not be observed. The distribution could be degenerate, so that people could know the type, but anyway. All right, so that's sort of roughly it. So just to give a little background, sort of the starting point for this, at least for me, is literature on dynamic elections with adverse selection that I've written on, and Dan Bernhardt has several papers, and Francesco Squintani has a couple papers with Dan on this as well. And this is a model, though, with just a single state. So the environment's not changing over time. And in that model, the focus is on these equilibria with a simple kind of partitional form. That's the picture at the bottom there. So if the policy space is one-dimensional, and there are 5 types of citizens with ideal points corresponding to these dots, you might have an equilibrium, for example, where so these arrows are indicating what policies politicians would choose. So you could have an equilibrium, for example, where the median type of politician is just going to choose his ideal point and get reelected. The extremists are just going to choose their ideal points, and they're just not going to get reelected at all. And then there's this interval in the middle here of policies that are sufficient to get reelected, and then I have these moderate types here. They're choosing between whether to shirk and just choose their ideal point and get kicked out, or to compromise and choose a policy closer to the median and get reelected. So in this kind of equilibrium, there's this nice trade-off that politicians are considering, especially these kind of moderate guys, voters 2 and 4 here. Should I choose my ideal point and just forget about the future and just have a great day today? Or should I compromise and satisfy the median voter and get reelected, but with a policy I like less? So there's kind of a nice trade-off there. There's also, so in that adverse selection model, what's sort of driving this equilibrium are the voters' beliefs about the politicians. There's a paper by Aragones, Palfrey, and Postlewaite, which shows that, well, you can do the same thing without the information part. It's a complete information model, but you just use history-dependent punishments, so to speak. And that's also a single-state model. When you go to a multi-state model, the adverse selection model just kind of blows up because the updating, you just can't, it's very difficult to handle in a multi-state infinite horizon model. So what we're going to do is basically say, well, the complete information model kind of mimics the adverse selection in the single state. So let's explore this in the multi-state setting. Okay. So that's where this paper goes, in this box. Now, to get that, that nice trade-off that I was talking about, though, we're going to have to, well, we could either use the history-dependent punishment sort of approach of Aragones, Palfrey, and Postlewaite. What we're going to do is just sort of take a shortcut, and we're going to assume what we call state-by-state commitment. All right? So what this means is that we'll begin a period in some state, S. The office holder will choose a policy, let's say X. Now, if the state stays S, we're going to assume that the office holder has to keep choosing X. So you can think about maybe the office holders choosing X means the office holder has made certain appointments that are difficult to change, or has made policy-specific investments, or maybe promises to unmodeled actors, and it's just difficult to change. So in that case, we'll say that the office holder is bound to X. But that commitment only lasts until the state changes, and then the office holder will be free to choose whatever she wants. Okay. So this is just sort of a reduced form kind of modeling assumption that we want to explore. Okay.
Does this create some incumbent disadvantage?
Does it create what?
Some incumbent disadvantage?
Incumbent disadvantage.
I mean, office committed to something. A challenger can offer something else that fits better.
So in this model, I didn't emphasize it when I went over the brief description, but the challengers are going to be passive, right? And so this actually helps the office holder because they can commit to doing something that the voters like if the state stays the same. So it's actually an advantage.
But why do you start from this specific example and you don't do the general case? Like,
General case?
What is special? Why you're starting? Is it easier to solve?
I don't know what you mean by general case. Which you're referring to?
Well, I guess most people would say the case in which you don't have this commitment.
And just use history-dependent punishments?
I don't know. I mean, you said this as a general approach or whatever, but it seems like this kind of adopt to this model, no? So I'm just wondering, like, is there an advantage? Like, it gives you something, like this buys you.
I think that there are pretty general conditions under which we could get everything that we get using history-dependent punishments, you know, penalizing flip-floppers. We have not written out a theorem to sort of see what those conditions are. I guess I kind of think this is an interesting modeling assumption to explore because it's sort of between the citizen candidate model where there's no way to commit at all, and then the Downsian style commitment where candidate is just making promises in advance of the election that they're actually bound to. And this is intermediate because the only way to make this commitment is by actually choosing the policy, sort of putting your money where your mouth is, so to speak. So it's this I think is a more palatable assumption than the usual Downsian one. And we thought this would be kind of nice to explore, but we will have to go through and look at conditions under which we can support this. So, yes?
If the state goes back to S in the future,
he's still free.
He's free.
Yeah. Okay, so I think I'm probably going to win the trophy for longest model description. Sorry about that. But the components of the model, so here I'm going to simplify things. The paper is a bit more abstract, but let's suppose that there's a finite set of voters and a countably infinite pool of politicians that's separate. All right, so you could think of a model where there's a continuum of citizens, and these are all from the same set, but let's just do this. Now, some ways in which the model is not general are we're going to assume that there's a finite set of types and a countable set of states. So this is a model of kind of lumpy information. But we're very general with respect to the policy space, which will just be a compact metric space, and the preferences of the actors. Okay. So let me tell you about the timing of the model, and I'll sort of fill in some of the missing parts as I do it. So we're going to start off in some period in state S, and the office holder's type is observed. The office holder will choose some policy X in a feasible set of policies. It can depend on the office holder's type and the state. And then people get utility from this. So if, by the way, I didn't say this, but the set of types, we're going to assume that voters and politicians all have types in this set. And since I'm just assuming a finite set of voters, we can sort of equate voters with types. And so I might, during the talk, sometimes talk about voters or types and conflate those. But okay, so an office holder, I don't actually know how to use the pointer on this thing, but this WT is the payoff to an office holder of type T in state S from choosing policy X. Now, a type T politician who's out of office or just a voter of type T will get the small u payoff. Okay. So this captures the citizen candidate style model where people have the same payoffs in office as out of office, but it also allows us to think about having office benefit and that sort of thing. All right, so after the payoffs are received, then we're going to draw a challenger from some distribution, this QT transition probability, and that challenger's type won't be observed. Okay, and then there's an election. Actually, for now, in this talk, I'm just going to assume that the office holder does seek election, so forget that. So we're going to have an election that takes place, and then we have an electoral rule, which we can be very general about at the sort of general theoretical level. So assume that there's a collection of decisive coalitions of voters, and if the voters who vote to re-elect the incumbent are decisive, then she wins, and otherwise the challenger wins. And then finally we draw a new state, and notice that the transition probability on states, this P function, depends on the current state and the current policy choice. It can even depend on the current electoral outcome. And then we move on. Okay. Yeah, Ethan?
I'm just wondering, for your results, would it be okay for the voter's utility function also to be directly a function of the incumbent's type?
Well, yeah. So again, our existence result is going to be very general. I'm going to have very modest characterization results. But for the existence result, we actually get that because the feasible set that the politician chooses from can depend on her type, right? So you can have some types of politician. Yes, it could be disjoint feasible sets, and yeah. So we get that in a sneaky way. All right, so then we move to the next period. So that's the setup. Some assumptions quickly. I've already said sort of lumpy information, finite set of types, and countable set of states. The feasible policy sets are just subsets of a compact metric space. So this could be a finite set, or it could be the usual spatial model, or it could be, tax functions. It's very general. The electoral rule obviously captures a lot of the special cases that we're interested in. The utilities, we're just going to make very minimal assumptions about. Basically, we need them to be bounded, and in each state, we need them to be continuous in the policies. And similarly for the transition probabilities, all we need is continuity. So this is kind of a different style of model with lumpy information and no convexity required, yeah.
So can it be deterministic? The transition?
Yeah.
Continuous deterministic?
Yeah, but it's, remember the state space is countable, so
Okay, countable.
yeah.
John, can you capture the limits in the state transition?
We could, but at some point I wanted to mention this. Probably I should just do it now then. So that state-by-state commitment assumption, that if the state is going to transition to a new state with probability 1, then that state-by-state commitment assumption doesn't bite at all, right? And so in a model where you want the state to change every period, we lose what that gives us, and this model or this framework is not good for analyzing those kinds of situations. So this, I think, is a nice framework maybe for looking at situations where there's an economic state that could stay the same, depending on the policy choice. It could stay the same, it could get better, it could get worse. That's the kind of application I think of with this model. But one where there's term limits and the state has to change every period wouldn't be good. Okay. Okay. So I'll talk about strategies then. So we're going to focus on sort of stationary Markovian strategies. And so we need to describe the policy choices of the politicians. So that's just going to be this pi thing. Pi t conditional on S is just the mixing probability of a type T politician in state S. Here we're imposing type symmetry as well. Notice it only depends on T. And we have our commitment assumption that I already talked about. And then for voting strategies, we take kind of a reduced form approach to modeling voting strategies. Instead of modeling the whole profile of voting strategies, we just kind of summarize it with this rho thing. Rho STX is going to be the probability that a type T politician is reelected in state S if she chooses X. That's just between 0 and 1. It is important that we allow for mixing. The way we do this mixing, though, is suppose a politician is elected for the first time in state S and chooses X, and then there's some mixing. Well, if the state stays, suppose that there's mixing and we re-elect the person and the state stays the same, then we're just going to keep re-electing. We're not going to remix every time. Yeah?
So it depends on T. I mean, is that a Markovian?
T is the type of the politician.
Right.
Yeah.
So X, T, what is X?
X is the policy choice. So it's in state S, this type T guy chooses X, and then there's some probability that they get reelected. So this is a reduced form. If we were modeling all of the voters' individual strategies, the mixing would be generated by indifferent voters.
But
Yeah.
So you don't have, because that makes things quite different, because in this case, is this, what is this coming from, this thing, this row?
The mixing from indifferent voters.
So the voters have an expected value function, and they
Yeah, I'll tell you the equilibrium conditions, but right now I'm just describing strategies. So actually I'll just do that. Forget that. So I have to define, to define our equilibrium concept, I need to give you 4 continuation values. It used to be 5, but I got rid of one last night, so. Basically the voters' continuation values are going to be the V's here. And there's 2 payoffs that voters have to evaluate. One is the payoff to keeping an incumbent, and the other is the payoff to a challenger. So the V with the superscript B is the payoff to, it's the following. So suppose we're in state S and a type T guy just chose X. Now if you re-elect this guy, the voter's discounted expected payoff is going to be this VB. And if she goes for a challenger instead, it's going to be the VC. Okay? The B means bound. And then we need to calculate payoffs for the office holder as well. So WB is going to be the payoff in state S to choosing X and getting reelected. And WC will be the payoff to choosing X in state S and then getting kicked out. Yeah, Ethan.
I'm confused about an assumption, which is this. So we have these Markovian strategies for the politicians, which are mappings from like my type and the state into actions. But then you have this assumption that if we return to the state later, I'm free to do something. And so it's like strategies are mappings from type strategies, type states and histories.
Yeah.
Any histories of paths of states or something like this?
Yeah, there is a more formal description in the paper, which I know you guys don't have yet, but you're right. So it's not exactly Markovian. It depends on whether you're bound or not, basically. In addition
to... I could redefine the state space to include sort of the
bound
states or something.
All you would need is to put in a marker that says whether the guy's bound or not.
I see.
Yeah. So it's pretty close.
But it is really not just from states as you've described it. It's from these.
Yes. It's as Markovian as you can get with this commitment assumption, basically. But that's a good point. Okay, so to define equilibrium, yes.
Even in some sense, it is a way of relevant variable, no? The fact if you're bound or not. So
it's path relevant?
Isn't it?
Yes, so okay, so people use Markovian in a couple different ways. So probably in the Maskin-Terol way, this is...
Well, I guess that's the way. I mean, if you need to define it in any way, you want to limit to payoff relevant. It's a bit arbitrary, of course, but
in stochastic games, it's defined with respect to an exogenous state space, which is kind of, it's terminology, but your answer actually sounds better, so it is Markovian. So I'll just go through this quickly because I think it's actually, even though there's notation, it's pretty intuitive. So basically, in equilibrium, we just want voters to be voting in a sensible way, and we want office holders to be optimizing. So what's a voter going to do? They're going to compare the payoff to re-electing a guy, the VB, to the payoff from a challenger, the VC. And the P set here is going to be policies such that the voter strictly wants to re-elect the guy. And the R set is going to be policies such that the voter weakly wants to re-elect the guy. And then basically, so I can probably just fast forward to this. So given strategies that, as I've described, we can calculate two sets, a P and an R. Okay, so the P set is going to consist of any policy such that there's some decisive group of voters that strictly wants to re-elect the politicians, right? So if you choose a policy in that set, you should get re-elected with probability 1. And the R set is going to be policies such that there's some decisive group that weakly wants to re-elect you. So if you choose a policy outside that, you should not get re-elected, right? And so that'll be this condition on voting strategies that we impose. So the second, so our equilibrium concept we're going to call simple Markov electoral equilibrium. The second condition here on voting strategies is just what I said. But other than that, if a politician chooses an X that's sort of weakly acceptable but not strictly, that means there's some indifferent voters, and we're going to allow the guy to be reelected with any probability between 0 and 1. And then the optimality condition for office holders is just the obvious one. That, yeah.
So you have some correlated equilibrium?
No.
So you said if they are indifferent, so it's at the individual level, so you can choose the probability at the individual level. Yeah,
when the set of voters is finite, we can just do that. You're right, if you want to have a model with a continuum of voters, then to get this, you would need to have some sunspots or something that people were coordinating on. Yeah. Okay, so that's the equilibrium concept. So results, I'm not going to try, well, we haven't really done as much as I would like in the paper, even though it's already pretty long. But basically, I'll give you the existence result, which is going to be very quick, because I wasn't really going to go through the proof. And then we have, then the next step is to try to characterize equilibria. And under these general conditions, you can't really, as far as I can tell, get very far at all. So we'll impose quite a few more assumptions, and we'll look at two kinds of results. So one is conditions under which there's a representative voter in a state. If you have these state variables moving around, the model's pretty complicated, so you would like to simplify elections. So we'll give some conditions under which we can do that. And then we'll talk about core convergence results, which is sort of a dynamic analog to the median voter theorem. So existence is just that there exists an equilibrium. And it's quite a bit of work. It doesn't follow from results in the game theoretic literature. It requires a precise selection of re-election probabilities. It's a very tricky part of the argument. It's worth mentioning that in these dynamic models of elections and dynamic models of bargaining, there often are really analogous results. I mean, there's often, if you write down a model of bargaining, there's almost a corresponding version of a dynamic election model to that. So this is actually kind of related to a paper on bargaining that I have, and the existence proof kind of uses the techniques there. But to give you just some idea of the complications, so here we have these, remember the transition probability on the states was endogenous, right? The X appeared in that. And so when you look at the objective function of the payoffs of the voters and the politicians, you lose, even if you start assuming concavity of utilities and all that, you lose those properties when you start thinking about the future and you have this X appearing in the transition probability. Anyway, so the continuity result, I'm not going to spend any time on because I think by now people kind of expect this thing, but at least it holds in this model. If we parameterize things in a continuous way, we get the usual upper hemi-continuity kind of result. Okay. So the representative voter theorem that we have is, I guess I should say what a representative voter is. So, so a representative voter in state S is going to be a voter whose preferences are basically determine the outcome of the election. Okay, so here's where I'm talking about types instead of voters, but voter type kappa is going to be representative at S if, for all t, she strictly prefers to re-elect the guy if and only if there's a majority or a decisive coalition that wants to, and similarly for weak. Okay?
So you can think about this, just there's only one vote.
Exactly. And actually for the dynamic core convergence, we'll just assume there's only one voter. Okay. All right, so when can we assume there's only one voter? Well, at least these are sufficient conditions. Let's assume that the policies lie in a one-dimensional space. Let's assume quadratic utilities. Okay. Now, for this is a limiting thing, which I wish we didn't have to do, and we could try to push it. I don't know if these techniques would help us, though. Let's assume that it's independent of the state. So the voters have fixed ideal points on the line in quadratic payoffs. And we're going to have to assume that the voting rule is strong. So just think about majority rule with an odd number of voters. That's the best thing to do, probably. And then the median voter, under this assumption, there will be a unique median voter. Let's call that guy kappa of S. And because we allow this voting rule, the electoral rule, to depend on the state, the median voter could be different in different states. Okay. So we're just going to focus on one state.
So you're just assuming there is a dictator in every state?
Well,
to put it in
Yeah, we will be assuming that. Right now we'll give conditions for it. Okay. All right, so suppose we have a simple Markov electoral equilibrium. Let's assume that we have these quadratic assumptions. Oh, I didn't mention we need to assume a common discount factor. So, I mean, these are fairly innocuous modeling assumptions, I think. So we'll assume those. We'll assume, let's say, majority rule n odd. Then the median is in state S will be a representative voter in that state. So they'll be like a dictator in that state. And of course, this extends to multiple dimensions if the core is not empty, but that's kind of a fragile thing. The proof of this, I mean, this kind of result comes up in other dynamic models of bargaining and elections, but and our sort of general approach is similar. Basically, what we do is we show that given an equilibrium, we can write these continuation values as integrals with respect to probability measures. So given ST and X, the voter's payoff from re-electing the incumbent can be written as an integral with respect to, say, mu, and the payoff from electing the challenger can be written as an integral with respect to some other probability measure. And then we use a theorem by Jeff Banks and I have in a paper in Social Choice and Welfare, which says that under these quadratic conditions, the median voter is always decisive over voting between pairs of lotteries. Okay. So, what we've shown here is that the election between the incumbent and the challenger is basically voting between a pair of lotteries, and we can apply that result. The tricky thing here is that to get this representation in terms of mu and nu, we need to use a contraction mapping argument. It's complicated because they depend on STs and Xs. So, but anyway, that goes through. And so we have some conditions under which we can simplify elections and just think, okay, in a state S, there's some representative voter. So for the core convergence results, we're just going to then say, suppose we have a representative voter in each state. Okay. So in the standard Downsian model, obviously everyone in this room knows, there's a unique equilibrium. That is that the two parties or candidates offer the median voter her ideal point, right? They basically do what the median voter would do if she could just choose policy directly. So we're going to try to understand when that would hold in this model, okay? When will politicians do what the representative voter would do herself if she could choose policy? So to formulate this, we're going to have to simplify the model a little bit. So, right, remember, these feasible sets could depend on the politician's type. Well, now we're going to say they're independent of type, and same with the state transition. So at least it's conceivable that the median could do what the politicians are doing. But even after that, there's a couple complications here, right, compared to the usual median voter theorem. So one is that, well, there could be different medians in different states. But the other is that what the median voter would do herself is an endogenous thing, because it's going to depend on what she would expect other median voters to do in other states. Okay, so to attack this question, we need to define an associated game between these representative agents. Okay, it's what you would think, I think. So in any state S, think about a game where the representative voter just herself chooses a policy, and then we draw a new state, et cetera, et cetera. Okay? So we want to know when the equilibria of the electoral model look like the equilibria of this representative agent game. One thing to note here is that if the representative voter is fixed across states, then this is just a dynamic programming problem. Okay? And this V star will come up later. That'll be the optimal value function for the programming problem. Okay. So we're going to, well, of course, there could be multiple equilibria in both models. And so now the question about, this sort of issue of the median voter theorem becomes kind of complicated. How do you actually state this sort of thing? Oh, I'm getting ahead of myself. Well, we're going to look at two types of median voter theorem. I guess before that, I should just mention, now we're going to start piling on some assumptions. I think if you look at each one, it seems okay, but sorry it's such a long list. Yeah.
This I'm trying to understand in what sense it's a court. So it's a state by state, right? So if you think about in your setting, you could have a mapping from states to policy. I mean, what is an allocation in your model or a policy? It's going to be a state contingent policy.
Well, I wouldn't.
There isn't necessarily a median.
I wouldn't.
State contingent policy, right?
So, this model generates a distribution over sequences of policies, right? And I'm not looking for a core in that space of sequences.
It's just a state by state.
Yes, and it's, that's a way of thinking about it. So we want to know, when in each state, the politicians in that state will choose like the meeting guy in that state.
Static, right, basically. Well,
it's not static because what
you're taking into account the future value.
Yeah, what the median voter would do in a state will depend on what she thinks other people will do in the future. So,
what's the practical use of this? Like, what do you get out of this?
well, obviously what we get out of this is since
representation, is it easier?
well, this would give you a way of solving the electoral game, right? So this representative agent game is simpler. First of all, there's no elections because we just have these dictators in each state, but there's no intervening politicians. Okay, so if there were a perfect correspondence between equilibria of these two models, you could just solve the simpler model, right?
Yeah, but I guess who is the dictator and the endogenous preferences would depend on the details of the model.
Yes, I mean I'm not saying that. Oh, I went.
The representation, but it may be very hard to
Yeah.
to have it right. Generally.
This model, this representative agent game, might not be that easy to solve, right? Now, in the case where there's a fixed representative voter, though, it just becomes a dynamic programming problem. So then you really get a lot of mileage, right? That's where we're coming from with this. Actually, good question. So here, the first couple assumptions I already made, actually, we're just going to assume, we're going to take the politicians out of this. We're going to assume that politicians have mixed motives, and for some things we'll be making B large. We will need the future to matter, so we'll assume that politicians have positive discount factors. They're not totally myopic. And there's a representative voter in each state. E5 prime is the one where the voter is fixed across all states, and that'll come up later. Okay. So maybe I should actually check the time. Am I doing okay?
7 minutes.
Okay. So, right. So as I was saying, we're going to look at two types of theorems. So what we'll start with is we're asking the following question. Suppose we have an equilibrium from this representative voting game. When is there a corresponding equilibrium in the electoral game? Okay. And it turns out that under these assumptions, if the politicians are largely office motivated, so if this office benefit is big, then we have a very general result, actually. Then given any equilibrium from this representative voting game, that's the pi tilde. Notice that pi tilde just depends on S. That's the mixing probability of the representative voter in state S in this game. So given any equilibrium from the representative voter game, there's a corresponding equilibrium in our game. Okay. And when I say corresponding, I mean that there's an equilibrium where in every state, all politicians implement the strategy of the representative agent, even though those politicians might have very different policy preferences. Okay.
But B is large.
But B is large.
So they could matter almost not at all, right?
Well, I'm not going to say, they sort of matter not at all, but you have to worry about the details a bit. So one of the issues here is that because the politicians can have different preferences, they're not going to be indifferent over everything in the support of this thing, right? The pi tilde could be a mixed strategy in this representative voting game, and we need to induce these politicians to mix according to that. So we need to make them indifferent over everything in the support, and we use the mixed voting to do that. Okay, and so we make these guys indifferent, and then because the office benefit's big, and then we will kick them out if they don't choose something in the support. The office benefit's big, so they're going to go ahead and do it. Okay. If there is a fixed representative voter across all states, then we can basically do this with pure strategies, not using that mixing. Okay. All right. So that's one side of it. I already talked about that. The other side of the analysis is we want to ask when this is true for all equilibria of the representative voting game. And here's where we're going to use the stronger E5 prime. That's where the representative voter is fixed across states. And here I would say we don't have the strongest results. The first one is assuming policy motivation and holds for high discount factors. And here I'll just tell you, without going through all of the details here, the idea is that now there's a fixed representative voter, so this guy can basically always just wait until he draws a politician of his own type. Okay? Once he draws a politician of his own type, he can just keep him, and that guy will solve the dynamic programming problem for him, and that's fine. So he could just wait until he draws a guy of his own type. That could be costly, right? Because you have to wait for a long time possibly. But if the guy becomes very patient, it's not that costly. So you get this result where basically this fixed representative voter can achieve something arbitrarily close to her optimal payoff. Now, this is for policy motivation with no office benefit. It turns out wrong way. You would think that if you made office benefit high that this result would go through. It turns out it doesn't. Here's a simple example. Those were supposed to be in colors, but are they? Because I don't see colors that well. Okay, good. So is there a red and a blue? Okay. So this is the simplest example that we could possibly come up with this. So now there's only one type of player, okay? In contrast to the last theorem, though, we're going to assume office benefit's high. There's only 3 policies, and you can see the ranking for the agents in this model is just z over x or z over y over x. There's a bad state and a good state. So it's pretty clear what the optimal thing for the representative voter would be here. In state B, the voter would choose Y, which is pretty good, and then transition to the good state and just stay there forever and get Z. That's supposed to be in blue. And then, but there's an equilibrium in this model that's kind of odd, which is that the politician in the bad state will choose X, which is the worst thing, because, so the politician will choose X and get reelected. I didn't put this in the picture. Okay, so the equilibrium is that in the bad state, the politician chooses X and gets reelected. In the good state, the politician chooses Z because that's the only possible choice, but gets kicked out. and replaced by a challenger. Now this is all optimal for the voter because all politicians are doing the same thing. The voter's indifferent between the incumbent and the challenger. And you can see why the politician would do this, because office benefit's high. They get reelected in state B but not in G, so you're going to stay in the bad state forever here. So kind of interesting complications come up in these models. What we have, I know I can sense I'm running out of time. We have a result that I'm not entirely happy with at this point. Basically, what's driving this is that there's some cases where, like in this good state, this politician, the incumbent, cannot get reelected. There's nothing she can do to get reelected. So if we only consider equilibria where you can get reelected, then we can kind of rule out the example I just gave you, although I'll just flag, I'm not crazy about this result yet because we're assuming that the policy, the state transition is independent of X. And anyway, but under certain conditions, we can rule that out and get the strong dynamic core convergence even with high office benefit. So is this a good time? Okay.